So this morning we finished off the evolution of vorticity. There was an issue of finding a boundary condition for the vorticity. The vorticity equation and the Poisson problem for the stream function are not quite decoupled because we don't get a boundary condition of the vorticity given by the physics. We have to invent one by some numerical games. There was an issue of we've discovered things were unstable if the time step was too big, and I operated 80% of the limit. And then I checked the results were accurate as they were supposed to be. For this nonlinear problem where I don't have an analytic answer, you can plot things of interest like the vorticity in the middle at time equals 1 and see how does that behave correctly according to the accuracy. And eventually we got results, the flow and the force on the lid. So now we're going over to what's called the primitive variable. It's the original variables of velocity, u and v, and pressure in this two-dimensional problem, just u and v. So you know the momentum equation. I've written it all out for u. There's the same equation for v. And the pressure, which is in the momentum equation, its job is to make sure the flow is incompressible. Because we can think about compressible flows where depending on how much compression there is, you get a pressure. Pressure is a function of density and temperature. And so the divergence of the velocity is the compression or expansion, dilation, and that is what determines the pressure. Except there's not a local relationship, it becomes a global relationship. You need the whole pressure field that makes sure the divergence of the velocity vanishes at every location. Okay, we start from rest. We know the boundary conditions on the velocity of 0 on the bottom and two sides, 0 for vertical velocity on the top, and a given tangential velocity on the top. So where do we get the pressure? Well, one answer is find an equation for the pressure. And we can find an equation for the pressure from the fact that the divergence vanishes, and so the divergence of the time derivative of the velocity vanishes. We know the time derivative of the velocity from the momentum equation. So if we take the divergence of the momentum equation, we get a mess. So here I've got the time derivative of the velocity is u dot grad u, gradient of the pressure and del squared u. If I take the divergence of du by dt is easy. Divergence of the pressure is del squared, of the pressure gradient is del squared p. Divergence of the divergence of the Laplacian of u, del squared u, is Laplacian of the divergence of u. And then there's the awkward u dot grad terms. When you take the divergence of them, there's going to be a u dot grad of the divergence, but then we have to differentiate also the first term, and that's what all this is with subscripts. The summation over I and summation over j. Now, so that's just the divergence of the momentum equation. We know the divergence of the velocity is 0. So we know the first term, left-hand side is 0. We know far right term is 0. We know this term is 0. So we've just got the del squared of the pressure is equal to that cross, where this is 0, that's 0. So we've just got del squared of the pressure is this cross gradient, this cross product of the velocity gradient. Right, so good, we've got an equation for the pressure. You notice the equation is a Poisson equation. You just can't get away from a Poisson equation. So in stream function vorticity, you've got a Poisson equation. In primitive variable, you've got a Poisson equation. And that's the thing which takes all the computer time. And it's unavoidable. Think of another formulation, and you'll have the Poisson equation there. So, right. So we've got an equation in the interior. What boundary conditions are we to apply? And you have to think about it carefully. And quite a number of people don't think about it carefully. So this is the answer, is you go to the momentum equation and see what's happening. So let's look on, here's our square box. And we've got x and y. Let's look on x equals 0, this boundary. On this boundary, we have no inflow, so u is 0, u 0 there, and there, u is 0 all the way along this boundary. what is the momentum equation or at a point on the boundary. Well, here's the momentum equation. du by dt is u dot grad u is minus gradient of pressure in del squared of u. And on the boundary, x equals 0, u 0. So the time derivative of u 0. U 0. The x derivative of u isn't 0. The velocity in this direction actually does increase away from the boundary. Well, it actually doesn't, but never mind. So I don't want to know. This is 0. U vanishes at all values of y, and therefore the y derivative of u vanishes. Equally over here, u vanishes at all values of y, so the second derivative of u with respect to y vanishes. So I've got all these zeros, and what have I got left? I've got the pressure gradient and two x derivatives of u. So when we've put all that's 0, that's 0, that's 0, that's 0, we've only got two terms left, these. So this is the x derivative of the pressure gradient out of the wall is equal to two x derivatives out of the wall. And in general, so I've just done this one boundary here, but it's true of all boundaries where there is no normal flow, u is the normal velocity, we can generalize this to being the derivative of the pressure in the normal direction is equal to the normal velocity, two normal derivatives of it. That's what we've got in this particular case, and it's true on all boundaries where there's no inflow. If you've got an inflow across the boundary, then you actually have to tell me the pressure. How hard are you pushing the stuff in? Okay, so here we've got a boundary condition. You notice it's a von Neumann condition. It's the gradient of the pressure. I don't know the value of the pressure. Pressure equals 1, nothing will happen. Pressure 1 everywhere inside the box, nothing happens. Pressure equals 10, nothing happens in the box. So there's an additive constant. And that's a little problem when you're like to plot out the pressure. It will have an additive constant, which is arbitrary. So as a little technique, if you want to compare one calculation with another, one resolution with another, it's a good idea to find the average value of the velocity and subtract it. So that you'll choose the additive constant, so the average pressure is 0. Okay, so if we take this equation for that equation for the pressure, del squared P is du by dx, and the boundary condition, and solve that, what happens is a disaster. This is, I'm plotting here as a function of time. What is the error in satisfying div u equals 0? So we start with nothing, so div u divergence of the velocity is 0 initially, and it just climbs. And it goes to a non-zero value. So this solving the pressure equation with the pressure boundary condition gives me a flow with the divergence equal to 0. It's a problem. The flow is also rather strange. It's not a flow that you can understand. The pressure field is pushing the flow around in a way that it is not pushing the flow around in a proper way. Something's all gone wrong. So I thought, have I made a mistake when I first did this? So did I make a coding error? So you check the coding, no problem. If you vary delta t, if it's a numerical error, have I made a numerical error here? So if I vary delta t, the answer ought to change. Doesn't. If I change delta x, does it change? Well, it changes a bit, but not by much. So it changes from 0.35 to 0.34. So we have a problem. The problem is that our pressure equation, here, we assumed div u is 0. Div u is 0. Div u is 0. Suppose we made a numerical error at some stage and it wasn't 0. This assumes it's 0 and it doesn't correct any error. So it actually has a nasty effect that the time derivative of div u is equal to del squared u. It may grow. So if div u is 0, it's okay. But if div u isn't 0, then there's a problem. So little errors, numerical errors have accumulated, and we get a nonsense answer. So that didn't work. Okay, so I have to think again. And I mentioned at the beginning, the pressure field is the Lagrangian multiplier associated with the constraint of div u is 0. And let's sort of think about it in a general sense. So out of all possible velocity fields, which I can only represent in 2 dimensions, out of all possible velocity fields, there is some surface, some restricted velocity field, this black surface here, where div u is 0. Off this surface S here, the div u divergence for u is not 0. So we start at some time level on the surface, hopefully, and then, without any pressure field, the time step, the derivative of the velocity would take us away to this point, take us away on the blue curve. And what pressure gradient does is it removes the component normal to the surface and puts us on parallel to the surface. So if we add the gradient of pressure, we move in a red line, which is tangential. So the job of the pressure field is to keep us on div u equals 0. Right, except if we have a first order time stepping method and we move in a tangential direction, we've come off the surface. And if we move in a tangential direction again, we slowly drift away. And we have to do better than that. So just doing simple time stepping and getting the correct direction that's in the direction of keeping div u equal to 0 is not right. We want to come right back onto the surface. So this is point C. So we don't go off on the tangential direction. On this curved surface, we have to end up here. So at the end of the time step, whatever, we don't mind even if we started off the surface. We have to make sure that at the end of the surface, end of the time step, we're back on the surface. So we correct previous errors. Okay. So that's the idea. And the way it's done is by a split time stepping method. So you first make a time step from time level n, start over here. Time level n, you make a time step forward to this intermediate starred velocity field, which doesn't have any pressure field. This has just got u dot grad u del squared u. The grad p is not in there. So we make a time step off the surface with without the pressure. And then the second part is to add to this the time step associated with the gradient of the pressure. And the pressure you want is such that the divergence at the new time is 0. So I ask that the divergence at the new time is 0. That will mean, so this divergence, this is 0. Divergence of the starred velocity is not 0. And that's going to be del squared t. So we get an equation, del squared p, plus the pressure is 1 upon delta t, the divergence of the starred velocity field. And if we can calculate that pressure, we can take that pressure, the pressure from solving this equation, add it, find out the pressure gradient, add it to the starred velocity, and we guarantee that divergence of time level n plus 1 is exactly 0. Okay? So this is self-correcting, previous errors get wiped out, and sounds great. Doesn't quite work, but it does eventually. This is right, this is a good idea. So, right, so what we have to do is to work out del squared of the pressure. So here's the sort of code. It's getting slightly messy by now. So the starred velocity field without the pressure has u dot grad u, that's u du by dx, v du by dy, and then the Laplacian of the pressure, this nice numerical molecule. So you can see here, there's the blue x's are the x variation, the i's are the x variation. So this is the u du by dx, and then the v, the blue, the green j's are the y variation. So this is du by dy. Right. So let's get into the half step. And then if we take that starred velocity field and work out its divergence, this is centrally differencing. This is the du by dx and dv by dy of the starred velocity field. That's the Laplacian of the pressure. We can find out some, we can solve the Poisson problem, and it sort of nearly works. The divergence of the velocity field that you get out of it at the next time step is nearly zero, but it's not quite zero. So, to some extent, I originally said, well, this is wrong, because it was all designed to make the divergence at n plus 1, 0. It's only made a small error. There's a small error in the momentum equation. They go together. Let's live with it. But no, we're supposed to have done it exactly. So what's gone wrong? Well, there are two terms in the divergence, du by dx and dv by dy. So this is du by dx, central difference. So it's I plus 1 and I minus 1 of the nu at the velocity at time level n plus 1. The velocity at time level n plus 1 is the star plus the pressure gradient term. This is the pressure gradient difference. And because I want the velocity un plus 1 at I plus 1, I've got the pressure at I plus 2 minus the pressure at I to be central difference. To get the pressure gradient at I plus 1, I've got the pressure at I plus 2 and at I. And then the pressure gradient at I minus 1 is found from the pressure at I 1 more, so I, and pressure at I minus 2. Okay, but you're supposed to follow this carefully. So to get the velocity at n plus 1, it's the star velocity plus the pressure gradient. And then I want this at I plus 1 and I minus 1. I plus 1, the pressure gradient at I plus 1 is I plus 2 minus I. Right. And there's a similar expression for V. And then when we put it together, we get a numerical molecule which is different. So before we had this nice compact one, which is just at I plus 1, I minus 1, J minus 1, J plus 1. We've now got the pressure at I plus 2, I minus 2, J plus 2, and J minus 2. So, that works exactly. Yes? So we first find out what the velocity is without a pressure gradient, and then we add a pressure gradient, not to be in the tangential direction, but to come down to here, which is div u divergence velocity at n plus 1 is 0. So the first one to star is to go from n and then make a delta t time step with no pressure gradient. U dot grad u and del squared u. And then the second step from star to n plus 1 has the pressure gradient in, and you choose the pressure gradient so that the divergence at n plus 1 is 0. Okay? And so divergence of that gives me del squared pressure is, and this will be non-zero. Okay, so this split time step is the way of imposing the exact constraint. And because of central differencing, this one didn't, and this one does. So this gives me the divergence of the velocity vanishes exactly, but it produces a mess. So the pressure field has got some pluses and minuses, and there are little pluses and minuses in the velocity field. And what has happened is that this numerical molecule has decoupled the even and odd grid points. So you can see that the grid point of interest, we use 2 ahead. So if this is even, that's even, that's even, that's even, that's even. So the pressure field is determined, I'm solving the pressure field here on the even points, and if I shift ij along 1, I solve it on the odd points, and I get 2 disconnected, they don't couple to one another, pressure fields. They just couple in the boundary condition. So that's the reason why I get this two disconnected solutions. Each of them looks quite nice, but if I plot them together, it's wrong. And a pressure gradient, I have this pressure that is plus and minus, plus and minus, plus and minus. When I do central differencing over 2, I get zero pressure gradient, zero pressure gradient. Of course, there's an enormous pressure gradient, but I can't see it with central differencing. Right, so eventually we can get there, and we need a new idea, which is called a staggered grid. The problem with this numerical molecule, it's too wide. I really want to pull it in so the adjacent pressures are connected to me, rather than being these odd and even disconnected ones. There's also, this pressure problem also has a problem at the boundary, because if this is if you're at the boundary, the point next to the boundary, this asks something 2 points the other side of the boundary, 1 point the other side of the boundary. So on the staggered grid, we have our mesh. There's a point ij, that'll be j plus 1, this will be I plus 1. And we don't have our unknowns, the velocity uv and the pressure at the grid points, but we think of them as being halfway up. So the horizontal velocity is in the middle of the box and is at j plus 1. The vertical velocity is coming in at the middle of the box at the bottom at I plus a half, and the pressure is in the middle, so that's at I plus a half and j plus a half. And that arrangement is quite good. The pressure in here and the pressure in here are just what you want for the horizontal pressure gradient. The pressure here and the pressure here are just what you want for the vertical pressure gradient. The velocity here, 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 and here will give me del squared pressure nicely. So it's all nicely set up for central differencing. And the divergence, that's the difference in the horizontal velocity and the difference in the vertical velocity, is all about the pressure in the middle. So the div u and pressure are sort of nicely all connected together. Okay, and this will give us a nice compact numerical molecule. Right, so we have this u, v, and pressure there, and on our square box there's a question of how do you fit the staggered grid on this square box, and the answer is inflow, the boundaries are the inflow. So in fact we do have 0 here, and then we have a box like that, boxes like that, so that the inflow boundary condition is tackled as 0, u is 0 here, v is 0 along the bottom. There's a question of the tangential boundary condition, because the tangential boundary condition is half a step inside. So the way we can apply a boundary condition that is 0 is we invent a fictitious grid block outside, one grid block outside. We have some ghost cells. And I have a boundary condition that the velocity here is the opposite to the one there. So I have a boundary condition that v at v at minus a half and some level j is equal to minus the velocity at a half and j. So this one is the opposite velocity to there. So halfway in between the velocity is 0. So we have to do that all the way around. So that's what, this is the no flux. This is the one I've just written down. There's one on the other side that the velocity down there is the opposite to the velocity up on just inside. And similar things on the top and bottom. Well, the top is different because you've got a boundary condition that there is a tangential velocity. Okay, so we have this staggered grid. Remember, I have my indices going from 0 to n rather than 1. So you're going to be minus. You've got problems. I can have negative indices. Sorry about that. Okay, so we've got this split time step. We make a time step to a starred state without any pressure gradient. And so that's the original velocity at level, that's the velocity at time level n, and delta t times. This is u du by dx. That's very easy. There's a problem with v du by dy. So here we want du by dy, so we've got u just above and below. That's easy. But the v, I don't have a v there. I have a v over there. So I actually have to take the v there, 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 and there, and average them to find the velocity there. So that's what's happening here. I've got a quarter of 4 v's to try and find out what the v velocity is there. There are other things I could do, and I should do, but I'm doing that. Okay? And then du by dy is easy, it's just the v. They're not random, they're solving a flow equation. The v velocities are also solving equations. So at every point the v velocity will be different? Yeah, it'll be slightly different, yeah, because it's not random, it's according to what the flow is, which is true. His point is, what if the velocity is in some other direction? Oh! So if we're here, so I've got a u velocity here, but that boundary condition is 0. But I do have a u velocity going in that direction there. And I've got vertical velocities there, 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 and there. I'm trying to say, please can the vertical velocity be 0 here? And the way I do it is to say, have a point outside the boundary. The point outside the boundary is the negative, the one inside. And then the linear interpolation is 0 on the boundary. And I have at some stage to use that value when I'm doing these big averages and things like this. Since the grid is very, very small, although this points to and D are slightly different locations, the grid is very, very small. You just take the vectorial sum of that and you get the direction of velocity. Yeah, this is all a little grid plot in a big flow. This is the best I can do with first order. Well, this is designed to be second order accurate. If I'd have said v is 0 there, it would have been a first order error. But by doing this, I become second order accurate. The primitive variable approach is complicated because you really do have to confront what is pressure doing. You do have to think about this projection so that you end up the time. You choose the pressure so that you end up after a time step with 0 divergence. And then you're pushed into a staggered grid description in order to be compact. So it really is much more complicated than stream function vorticity. The commercial codes are doing this, don't worry. So the incompressibility turns out to be nice. That when you work it out, it becomes a nice compact operator. It's not, it involves just I plus 1 and I minus 1, j minus 1 and j plus 1. so that I don't get disconnected even and odd solutions. There is a problem of getting the pressure boundary condition, which is the normal gradient of the pressure is equal to the viscosity, which is 1 upon the Reynolds number, times the true normal derivative of the normal velocity. So this is a second derivative I want on the boundary, and I don't have any points. For the velocity u here, I only have u velocities on the interior, and I want the second derivative. So if I take these 3 points, I can work out the second derivative central difference accuracy there, but that's not there. So I actually have to use 3 velocities to get a second order accurate estimate of the second derivative of the velocity. So that's why there's a big mess there. So it's taking not only the 0 velocity, but it's 1 velocity in, 2 velocities in, 3 velocities in, into the interior. It's a one-sided second derivative. Okay. So when you write this, it does behave itself. The pressure field is nice. Divergence of velocity is 0. But it's not quite, it's not 0 at the, near the, right on the last square. And there is still one more thing you've got to do to get this right. And that is, because of this split time scale, we make a time step which doesn't have the pressure gradient, and then we correct it to the second step with adding the pressure gradient to get divergence equal to 0. The boundary conditions, we just leave the velocity u equals 0 there. But unfortunately, next to them, we're using a pressure gradient in the second step. So what you have to do is you have to satisfy the momentum equation on the boundary and time step the u equals 0 on the boundary to a non-zero value, so you can then apply the pressure gradient to bring it back to 0. Right. And when you do that, the divergence of 0, the divergence of u has been 0 on the interior, and it now becomes 0 on the boundary. So you're done. Okay. I've not found any book that's explained this carefully. Someone asked about a book. I'm afraid there's no book that I like. There's a lot of books. Well, there's a lot of very, yes. If you're prepared to buy about 20 books and only read 2 chapters of each book, you can find everything I've said. It's quicker, you can find it on Wikipedia. If you know the key words now, you can find someone else's version of this. And I am translating all of these transparencies into a real book. And it's 16 out of 17 chapters have been written. There's 1 to go. And there's some errors in it still that need correcting. Right. Yes? Yeah. Yes. Yes, yes, yes. Yes, you'll find lots of people say the normal gradient of the pressure is 0 in numerical calculations. It's wrong. You go and look at any analytic flow you know, Stokes flow past the sphere, you know, the normal gradient isn't 0. There. Yes. Yes, this is the boundary condition. And it is the normal derivative of the pressure is not 0, like many people use, but is the viscosity times the second derivative, the second normal derivative of the normal velocity. That's its no inflow boundary conditions. Lots of people look at the split time step and say, well, we've got to arrange that. Okay, It's connected with what I was saying before. So many people look at the split time step where you make a first time step with no pressure gradient and then you add a pressure gradient and realize that adding the pressure gradient will make the normal velocity non-zero. So to stop the normal velocity, normal velocity becoming non-zero, you have to make sure the pressure gradient is zero. And I'm saying, no, you don't do that. In the split time step, in the first part, you make the normal velocity non-zero, so that the pressure correction will put it back to zero. Okay? And it's a sort of delta x error, erroneously putting the normal pressure gradient to zero. Well, it's worse than that. Just look at an analytic solution. You find me a flow with a normal gradient of the pressure zero. It has to be a viscous. We're nearly finished. So it is very painful, the primitive variable. You have to really understand what pressure does, and then you're into this staggered grid considerations. But then it does work. So this is my velocity on the mid-plane. So at x equals 0, the top is going one way and the bottom is returning negatively. Most of the flow is actually negative. There's a very high velocity next to the wall going in the positive direction, and then there is a much smaller velocity which, to have the same amount of mass flux, has to be spread over a deeper region for the return flow. And those are the solutions of grids. I can read the scale. The red line is 30 by 30. The green dots are 20 by 20. The blue stars are 14 by 14. And they all superimpose near enough. And in addition, the red squares are the result I had this first thing this morning by the stream function vorticity method. And that puts you in a very powerful position if one code based on stream function vorticity gets the same answer as another code, totally different code, is agreed written by the same silly person, but the same different code produces the same answer. Okay, it might be right now. Okay, we have something new. We have the pressure, which we didn't have with the stream function vorticity. So this is x is 0 is here, and y is 0 along the bottom. The top plate is over there. I'll do it on this one over here. This is the top plate over here. This is y equals 1, going from x equals 0 to x equals 1. And you can see that there is a negative pressure over at x equals 0, y equals 1, and there's a positive pressure at y equals 1, x equals 1. So we have this square box, and the top is going this way, and we have a plus pressure over in that corner, and we have a minus pressure in that corner. And you have to think, is that sensible? Well, it is, isn't it? So here we have this box. There's a plus pressure up here. That's because you're sending flow at it. It's got to go somewhere. The pressure has to make sure the mass flux is sensible. So you have a high pressure up there to push it down. Equally, up over here, on this other side, we have a negative pressure. We've got flow going sideways. You've got to supply it. You've got to suck it up with a negative pressure in that corner. So that's why we've got a negative pressure over there and a positive pressure over there. So that sends them like that. And then there's a little problem. We've got to reverse the flow underneath. So there is a very small, no, there's not. It's still positive over there and negative over there. Oh, that will drive, that drives the return flow. Okay. So the positive pressure on this side and the negative pressure on this side, it's not much of a pressure gradient, will drive the return flow along the bottom. And it's the wall on the top, rather than the pressure gradient, that's driving the flow sideways on the top. Okay, get some numerical answers, try and understand it quickly to make sure, is that a test, is it? So I didn't tell you, but there's all these accuracy tests, and I've done the accuracy tests on this code. And I know this time step stability criterion as well. So I've done all those routines, because I always do them. And to calculate the force on the lid, we want to have the tangential stress, the viscous tangential stress. That's easy because we want to have the y derivative of the velocity, and on my staggered grid here, that's all lined up. So here we have a horizontal velocity. We had a boundary condition that the horizontal velocity was minus here, so we have no slip. Well, we don't have no slip. There's plus the prescribed velocity there. But because from the difference of those two, I can work out the gradient, central difference on the lid itself. That's very good. So this is my velocity at one step, the ghost point outside, minus the point just in half a step inside. That will give me central differenced second order accuracy. And then I want to sum all of these, so I integrate by multiplying them by delta x, that divides by that there. And I get, and I can also work out the viscous force, which I didn't do on the bottom. And there's something new, because we've got pressure forces, we can work out for the horizontal momentum equation, what is the pressure, we're driving this, what's the pressure on this side and the pressure on this wall? So the pressure is at a staggered point, so I actually need the pressure here and the pressure here and take the average to find the pressure there. So I can work out the pressure force negatively there, pushing it negative direction, and the pressure there, pushing it in the positive direction. So this is the positive pressure, that's the negative pressure. So we've got the pressure gradient. So when I come to this calculation of the force as a function of the numerical resolution delta x squared, the red curve is the viscous force on the top. The blue curve is the sum of the pressure forces on the sides and the viscous force on the bottom. The viscous force on the bottom is about a quarter. The viscous force on the top is about 4. So there's not much viscous force on it, but there's quite a significant pressure, because actually the sum of the viscous force on the top, bottom, and the pressure forces has to sum to 0. Because it's the momentum inside the box isn't increasing. There's no forces. So they don't quite agree because there are numerical error differences, but there's a very small difference between the force on the top and the force on the walls on the bottom. And the purple curve is the stream function vorticity result, which at these resolutions wasn't, at the coarse resolutions is not very good, at the fine resolutions is, and they are roughly linear, And I can extrapolate to get a 4-figure accurate, well, yeah, it's about a 4-figure accurate answer for what the force is on the bottom. What the force is on the top and the force is on the bottom. Okay. So, there's a lot there. Does someone want to ask a question which will make me explain it better? They're wrong. So they're wrong to say the pressure gradient is 0 there. You can ask, if I have a box and I'm solving Laplace's equation and I put the wrong boundary condition in, how much does it change the answer? It tends to change the pressure over here a little, a few percent. So you can probably tolerate that. They do have to confront the fact that they're wrong. You just look at an analytic solution, it's wrong. The analytic solution will show you the pressure gradient at the boundary is not 0. If you impose the pressure gradient is 0 on the boundary, you've done something wrong.
What happens when you have an inflow boundary condition?
If you have an inflow, you have to tell me what pressure are you applying to push it in. And then I have a pressure boundary condition. Yep. So if you think about a pipe flow, you can impose an inflow here. You automatically get the same stuff coming out if dvu is 0. And you would calculate the pressure difference. I think on the solving the flow will calculate the pressure. So I rather like the idea that I know I have to push it in with the pressure, and then if it's coming out, I'll find out what the pressure is. I can calculate then, numerically or theoretically, what the pressure is at the exit to get the pressure drop.
In general, we know the velocity, the inflow rate,
Yep.
but we generally don't specify the pressure at the boundaries. So what I've seen the Dirichlet pressure is zero if they are using the inflow velocity. So they are wrong in doing that.
Well, you know in a pipe flow there's a pressure gradient down a pipe. That means the normal velocity, the normal pressure gradient is non-zero, doesn't it, at the entrance?
And that is true. But they are not using the normal gradient of pressure. They are using a Dirichlet boundary.
Oh, so you're right, as I said. In that case, yes. I said for no inflow, there's this normal pressure gradient that you can calculate. If there's an inflow, you specify the pressure.
It can be any number, or you have to know the exact number.
Well, you could put it equal to 1 if you like, and then you'd find, or 0 would be the most sensible thing, 0 pressure. And then you'll find downstream, at the exit of a pipe, there'll be a -5 pressure. So you can calculate the pressure difference, and actually the value of the pressure is sort of meaningless. But the proper...
Using their Dirichlet boundary condition, okay, but the normal rate is 0 for
At an inflow, you should specify the pressure, which is Dirichlet. Sorry? Yes, you have to specify the incoming flow. So at an inflow boundary, you have to tell me all the components of velocity, the normal components and the tangential components. You normally say they're zeros, but you don't have to. They may not be zero. And you have to specify... At an inflow, you don't know dP by dN, but you go to a pressure condition, to a value of the pressure rather than a pressure gradient at an inflow boundary.
Clarification. Try to follow your argument going from 2, 3, and then 4. 2 is clear. I think I asked you earlier that should be forward referencing on the bound. It's in order delta x. Then you said let's go to algorithm 3, where now you do central referencing everywhere. When you did that, you started having these disconnected nodes. That's just plus, minus, plus. Take the pressure difference, very large. Now you get 0.
Because
Then, so algorithm 4 was, let's have a staggered.
Great. So the staggered grid takes algorithm. So algorithm 3 had this wide numerical molecule that had disconnected even and odd modes. And to make a compact numerical model, you have to get the variables closer together, which you do by this staggered arrangement. And it's very interesting that staggered grid improvement that is available in finite differences, there is nothing corresponding to it in finite elements. So finite elements always have spurious pressure modes, which you have to handle by some other method. But you can get rid of them totally by a staggered grid with finite differencing. Okay, so to recap, there are 4 algorithms. Algorithm 1 used the pressure equation, but it did assume the divergence was 0, and unfortunately, after a time, it wasn't 0, and it never made an attempt to correct it. 2 chose the pressure gradient so that the divergence was 0, but it said it was del squared p, and I know how to handle del squared p with a nice compact operator. And unfortunately, when you're central differencing your div u, it's not quite the div. You want this wide numerical molecule to represent it. And if you take the compact del squared u, I know what del squared del squared P is, you don't quite numerically get div u equals 0 out of it. So you have to follow very carefully the velocity you're putting into the divergence of u star to work out what the equation, the pressure, the numerical equation the pressure is solving. So analytically the pressure is solving del squared P, but the numerical version of it could be a wide grid, a wide numerical molecule. If you take a compact one on a regular grid, you're not doing the right thing numerically to get numerically div u equal to 0. It's horrible. So algorithm 4 has a compact molecule and it's getting the right divergence, and it's done it by having a staggered grid. And then there's added to it this problem of what is the boundary condition on the pressure, and it is not the normal pressure gradient is 0, but is you have to do a forward half step, the first part of the step of the boundary for values away from their boundary condition that they're 0 in order to come back correctly. Okay, so we've done a simple problem. I fear it's not quite as simple as you might have thought this morning, this second one. Things are getting more complicated now. So we're going to specialize, look at finite differencing, a whole lecture on finite differencing and higher order methods and conservative methods and lots of other fine details, more advanced detail. Then we'll do rather leisurely 2 lectures on finite elements. There will then be another one on spectral methods, the third way of representing the unknown velocity fields. And then time stepping, we've just done simple forward time stepping. There are lots of alternatives, and you wouldn't use them on the alternatives on the Navier-Stokes equations, but fluid dynamicists solve time-dependent equations for other reasons, and so you should know about other time methods, time-stepping methods. And then all the time we've had this Poisson problem, and there are other linear algebra issues, so I'll have a whole lecture on quite advanced linear algebra. So first year undergraduate, AX equals B, you would be amazed how sophisticated you could get on solving AX equals B. There are whole books devoted to it. And there's also eigenvalues come into linear algebra, which we have to